Welcome to Profen Tech Days. Welcome to today's webinar where we will explore a groundbreaking technology and an innovative company. I'm Sadettin Avcılar, your host for this presentation. Let me introduce you to Optical Zono, a visionary organization bringing innovation to the telecom and defense sectors. With a commitment to excellence, they have been pushing boundaries and transforming the RF over fiber and distributing field for 3 decades. Now, let's focus on the star of the show, the lead RF over fiber technology of Optical Zono. It's set to revolutionize the RF over fiber and the transmission. With unique features of like RF over fiber and fiber transmission, it's a game changer for the telecom and the defense sectors. Optical Zono has invested in research and development and creating a user-friendly, scalable solution. They prioritize customer satisfaction and offer dedicated support to maximize the potential over the RF over fiber technology. The impact of the RF transmission over fiber optics extends beyond individual businesses, benefiting the entire telecom and defense sectors. It brings change the way of operation in telecom and defense market operators. It also opens up new opportunities for growth and innovation. In conclusion, Optical Zono and their RF over fiber solutions represent a giant leap forward. Connect with their representatives like Profen to discover how it can transform your business and contribute to the advancement of the RF and telecom industries. Our webinar is titled RF Signal Transport Challenges and RF over Fiber Solutions. Our speaker is Britt McGinn. He is Sales and Product Manager of Satcom Department of Optical Zono. Now, I want to give the word to Britt. Britt, it's over to you. Please start your presentation.
Very good, thank you. Let me share my screen. Bear with me one moment. All right, very well. Can everyone hear me? Okay, so once again, I'm Britt McGinn. I am the sales and product manager for Optical Zono, in particular, our military and defense products and solutions. I'm going to give an overview primarily of applications today, but also as well some of our solutions that help solve signal transport problems. So Optical Zono, we're a US-based corporation. We're located in Southern California. We do all of our design, manufacturing, and test at our headquarters in near Los Angeles, California. We're a privately owned company. We have no debt or outside investors, and our 2 company principals, they have a long history in the fiber optics business, and they are still very hands-on and involved with the company. So we have a significant IP portfolio of intellectual property. That's both in RF as well as a data transport. I'll touch on that briefly. I'll concentrate on the government sector today. However, roughly half of our business is also for the telecom market, for the large North American wireless carriers like AT&T, Verizon, and T-Mobile. So this is kind of a sampling of our sorts of government and defense customer base. Why use RF over fiber? Well, the primary reason to use RF over fiber is for RF signal transport over long distances. One of the basic applications for long distance signal transport is antenna remoting. So Optical Zonu offers solutions for transporting RF signals as low as 10 kilohertz and up to as high as 50 gigahertz. So, this sort of technology is used in, big teleports and ground stations. Can be used by entertainment and broadcasting. That's not a large part of our business. Much of that 75 ohm, but we do part of that as well. We do fiber delay lines, which are used very extensively in radar and phased array antennas. There are some applications where a very weak signal has to be exchanged with a satellite constellation that is either low Earth or middle Earth orbit, such as GPS or satellite phones. And fiber optics is an ideal way of getting those weak signals from an antenna that has line of sight communication with a satellite constellation and distributing that signal into a building or into a tunnel or mine. So that's another application of RF over fiber transport. I'll go into those a little bit more in detail. Perhaps you cannot see these, and I can share these slides later. Perhaps you can't see the detail on the particular slides I'm showing here, but of course, coaxial cable has a, depending on the quality and the type of cable, has a certain attenuation that accumulates over distance. So, for example, at 3 gigahertz, a LMR 400 cable would have about 8 dB of RF attenuation. And for longer distances, of course, that accumulates. And the effect of RF attenuation is much more severe as RF frequencies get higher. So these top, and as that can be demonstrated by the fact that these attenuations get higher as RF frequencies get higher. Fiber, on the other hand, has a low and fixed attenuation that is independent of RF frequency. The attenuation of fiber is approximately 0.7 dB per kilometer. So one can go long distances through fiber. We have various configurations of equipment, particularly for antenna remoting, that can transport signals, uplink and downlink signals from an antenna to a network operating system. So in the very simplest case, that can be done with just little indoor flange mount modules. But for perhaps more sophisticated systems, one may want to install an outdoor enclosure directly on the antenna to transport RF signals, uplink and downlink to a network operating system, a network operating center. In addition to antenna remoting, one may simply wish to pass signals between two buildings. So Optical Zonu offers also rack mount solutions for transporting signals, in this case, up to 6 gigahertz between buildings or between sites. In a chassis such as this, one may transport up to 8 signals, 8 separate signals, either uplinks or downlinks in either direction. And those we can use wavelength division multiplexing, much like one uses frequency division multiplexing in RF. We can use wavelength division multiplexing to send combine all of those signals onto a single fiber. More sophisticated systems, Optical Zonu has 19-inch rack mount 1RU and 3RU chassis for connecting to multiple antennas or antenna sites that have much more than 2 or 4 uplinks or downlinks. We can transport out also 10 megahertz very low phase noise reference clocks to antennas for block up converters and low noise LNB block down converters for doing frequency conversion at the antenna. Moving on to more sophisticated systems, Optical Zonu offers a more sophisticated 3RU chassis that can accommodate up to 16 plug-in modules in the front of the chassis. These modules can be each one of 16 modules can transport 2 signals, either uplink or downlink. And these are still primarily in the frequency range of less than 6 or less than 9 gigahertz. For higher frequency signals, we cannot, the modules are much more sophisticated and larger, so we can't get as high a density, but we do have plug-in modules that can send up to 50 gigahertz up and down from antennas. And we use slightly larger and more sophisticated outdoor enclosures at the antenna to transport those signals. We can transport Ethernet over fiber as well to the antenna for purposes such as doing antenna control and doing remote monitoring of the equipment at the antenna. Let's see. Again, this is inter-facility links. We can incorporate managed switches within these 1RU 19-inch rack mount enclosures also to control RF gain in both the fiber optic RF transmitters and RF receivers. We can send timing signals as well. In addition to RF over fiber, we can transport RS-232 TTL timing signals such as pulse per second and IRIG-B timing signals. So in many cases, those are useful at the antenna. I'd mentioned before that we can multiplex multiple signals using different wavelengths onto a small number of fibers. So I'm showing here an illustration of a chassis where we're using coarse wavelength division multiplexing for, in this case, we have 8 signals here on 4 modules. And we can combine those together within a wavelength division multiplexer and combine all 8 signals and transport those on a single fiber. In addition to combining RF, we can combine the timing signals and the Ethernet as well, and the low phase noise reference clocks as well. So all of those signals can be transported on a single fiber using coarse wavelength division multiplexing, CWDM. Just from more of a product point of view, we also have very small plug-in modules for transporting up to 6 gigahertz. So in this case, I don't know if you can see the slide very well, but there are 4 within one one module insert card, we can transport up to 4 uplinks and or downlinks up to 6 gigahertz. So in this case, we're showing, transport of 16 6 gigahertz signals in the front of a single 1RU chassis. So signal density. Many applications require redundancy. So one of the things that optical ZONU also offers is 1+1 redundancy, where you essentially have a spare fiber optic link for each signal. We can also accommodate N+1 signal redundancy. So in that case, the example I'm showing here is for a 3+1 redundancy. So in this case, you have 3 signals and 1 hot spare transmitter or receiver that can be swapped in if any of the 3 primary signals are lost for some reason. So here's an example of a 3+1 redundant architecture where, let's see my cursor, we see one of the transmitters has failed at, here we go, one of the transmitters has failed on the transmit side. The other 2 transmitters are fine. However, the hot spare, the 1 spare transmitter, is swapped in. The RF signal is swapped into this transmitter and transported to the corresponding receiver on the other side of the fiber optic link. So the transmitter sparing is done independently or transparently to the receiver side. And likewise, redundancy architecture handles if a receiver fails, perhaps at the network operating center. So in this case, signal is rerouted to a spare receiver module. And it's probably too small for you to see on this particular slide, but in this case, signal 2 of 3 is being routed through the system. There's an issue. There's a problem with receiver number 2, and the signal gets routed around to the spare receiver and then back up to the appropriate output. So N+1 redundancy, that is an important feature for some critical applications that cannot sustain any signal transport downtime. We don't just, it's not necessary to, although in most cases people do down convert their higher frequency signals to, in particular, L band, but it is possible as well to transport higher frequency signals over fiber as well. So we have a case, we have a nice design win with the US Navy. This is kind of an illustration here of signal transport at KU band, or around 15 gigahertz. So the signal is not down converted. The radome or the antenna on the ship receives KU band, and then that signal is transported over some distance from a radome high above the ship's surface down to a equipment room, an equipment rack that is far below the surface of the ship. So KU band or higher, KA band as well, RF over fiber transport. So transport distance is probably the basic reason one would wish to transport signals over fiber. Another reason is just taking advantage of the fact that fiber does not radiate electromagnetic energy. All of the actually light is an electromagnetic signal as well. But all of the light is contained and trapped within due to the nature of fiber. All of the radiation is contained within the core of the fiber cable. So there's no RF emission when one is transporting an RF signal over fiber. So a very common application for such a capability is in government situations where there are skiffs or very secure areas that RF signals enter and exit an area, but they must be very secure and cannot radiate RF energy for the purpose of just security reasons. So that is another application for sending RF signals over fiber. There are certain additional benefits to that as well. Fiber transport is much less susceptible to, for example, lightning strikes. It is much more difficult to interfere with RF signal transport over fiber in the presence of lightning strikes. There are no ground loops in transport over fiber. When one's transporting over coaxial cable, each end of the cable must be grounded, and it's very difficult to get those ground potentials at the same potential. So there are ground loops. So there's no such issue in transporting over fiber. Fiber does not need to be grounded. Another application that we do, particularly with the National Security Agency, the NSA in the U.S., is doing very secure Wi-Fi distributed antenna systems. So essentially getting secure or secret signal transport into and out of areas that have distributed antenna systems. So essentially it's the same idea, secure signal transport over fiber. Another application that takes advantage of the very light weight and small size of fiber is for the purpose of getting signals to and from a tethered drone or an aerostat. So let's show a couple of illustrations here of what's essentially a deployable antenna. So in this case, a drone or an aerostat would just have a tether where signals are transported up and down over fiber. And optical ZONU makes some very small size, weight, power form factors of RF signal transport that are suitable for aircraft and drones. So I'm going through this kind of quickly. I can certainly share more detail with anyone afterwards or offline. Another application of fiber that takes advantage of the very small size and weight of fiber are fiber optic delay lines. A primary application that optical ZONU fiber optic delay lines are used for are for doing wireless system simulation, delay simulation, and for doing radar system calibration. So if you can see this slide, this form factor here, it's essentially a fiber optic transceiver with a coil of fiber on top. So essentially one can, in a form factor this size, and this is something I can hold in the palm of my hand. In a form factor of this size, up to maybe 15 kilometers of fiber can be spooled in a size such as this. So one can realize an RF signal delay of, perhaps 60 or 70 microseconds with a spool of this size, a fiber spool of this size. So essentially this delay line, it's a fiber transceiver. You put in RF, it's converted to fiber, it goes through a long fiber spool, and then is converted back to RF. So essentially what a delay line such as this, or any delay line does, is give you a delayed version or a delayed replica of your RF signal coming out the other side. So in a size such as this, we can do 60 or 70 microseconds of delay. Longer delays would require perhaps more of a rack-mounted system that can accommodate more fiber and longer delays. Well, this is an example of such a system here that one can build with longer delays, the delay spool being in this black chassis. This is an example of a switch delay. So in this case, there are multiple delay spools within a chassis, multiple separate delay spools. And we can use optical switches to switch in and switch out delay spools. And in that way, one can switch and switch between different temporal delays for the RF signal. So this is a more sophisticated system for doing switch delays, variable delays.
Britt, why do we need delays there?
Sorry, say it again.
Why do we need delays? To synchronize the timing?
Yes, a primary application of ours is for doing radar system calibration. So, one needs to, and that's for, manufacturing and test in particular, and it's done in the field as well. But if one needs to, recalibrate their radar system, this is essentially a fixed delay with which to compare your system delay and tune your system delay, however one does that.
Thank you.
Yes. So as I mentioned earlier, another application for doing fiber is for the case where one is receiving a line of sight. One requires a line of sight to a satellite constellation in order to receive, to send and receive a signal. And a good example of that is satellite phones, where Iridium or Global Star satellite phone, in order for one to use that, normally one has to be outdoors and be in an area, kind of an open area, where there's a line of sight to the satellite constellation that's going overhead. So in order to use a satellite phone indoors or underground or in places that do not have a line of sight to the satellite constellation, one may distribute those signals. In the case of satellite phones, an uplink and down, a send and receive signal. One may distribute that over fiber into certain areas of a building. So in a case such as this, one may have in a room inside of a building, one may have a fixed satellite phone cradle or harness that we can connect to the antennas outside over fiber. One may also have a system where the signal from the outdoor antennas is actually re-radiated wirelessly using re-radiating indoor antennas that are connected essentially over fiber to the outdoor antennas on a roof. So this is an example of satellite phones. Similar application, and this is an application that's used widely by our wireless telecom customers, is the transport of received GPS antennas, received signals from GPS signal constellations. Those are received by antennas on a roof and distributed into a building. So in the telecom applications, those are synchronous systems. Each base station or each re-radiating wireless radio within a building requires a timing signal to synchronize with the network. So a way of distributing timing signals to those multiple base stations is over fiber. And those GPS signals, it's much simpler than the satellite phone. This is a one-way signal transport. So it's much easier to split those GPS signals, split the fiber, and send that fiber to multiple locations, multiple rooms or floors within a building for transport over fiber, and then converting back to an RF GPS signal for a GPS receiver. So that's GPS or any sort of timing signal. I'll just quickly go through this. This is more of a product thing, but Optical Zonu, all of our equipment, except for the very simplest modules, have a very sophisticated remote management and control capability. So we have two types of managed switches, and that can be integrated into our equipment, and we can communicate with those in multiple ways, and all of those ways essentially are riding on top of SNMP version 2 or version 3. So one may actually use just one managed switch to monitor and control multiple chassis over SNMP. We can connect a single switch, a single IP address that one would connect to over a browser. We can connect that to multiple chassis via just going through a multi-port USB hub. So communication to multiple chassis is over serial USB. And on top of that SNMP Ethernet transport, we can provide a graphical user interface for all of our equipment, or a simple just a web user interface, which is essentially a table presentation of the SNMP MIBs. So these are hierarchical. In this case, if we're connecting a single managed switch to an entire rack of equipment, we can see the entire rack of chassis, and then we can drill down to single chassis, and then drill down further to single modules within chassis. So this is essentially our user interfaces that ride essentially on top of SNMP. Now, this is more of a detailed view of drilling into one of our chassis and monitoring a power supply or a switch or RF over fiber signal transport plug-in modules. And these are the various form factors that we offer. I won't talk too much about products. I'm trying to keep this more to the applications. But Optical Zonu offers everything from small little OEM board level fiber transmitters and receivers that one could take and design into your own equipment. And we offer indoor flange mount units as well with more rugged housing. And then at the highest level of integration, we can offer plug-in modules that plug into 19-inch racks that can be monitored remotely. So multiple form factors. I'll just very quickly touch upon as well, one of our patents is for a micro OTDR, a micro optical time domain reflectometer that we integrate into an SFP fiber data transceiver. So many people, there are probably hundreds of vendors that manufacture MSA transceivers, 2.5 gigabit transceivers, 10 gigabit, and much higher frequencies these days. But Optical Zonu integrates a micro OTDR into a small form factor pluggable. So what's the benefit of that? Well, here's an example of a couple of our managed switches in a chassis located in one perhaps part of town, and another chassis in another part of town, connected by perhaps many kilometers of fiber. Now we can multiplex onto this RF traffic, as I noted earlier. We can multiplex onto this Ethernet data signal as well. So when that Ethernet data signal is provided by one of the Optical Zonu small form factor pluggable transceivers that has the integrated micro OTDR, in normal operations, Ethernet data passes. But in the event that there's a fiber break, the SFP switches from just standard Ethernet transport mode to a micro OTDR mode. And instead of sending user data, the SFPs switch over and send out short pulses, much like an OTDR, either RF or optical.
Britt,
And
we
in
have
this,
a question here.
yes,
You were telling there are two transmitter and receiver, and there is a fiber line.
yes.
The question is, how far can one transport RF over fiber can go? Is it 50 kilometers or 100 kilometers?
Oh, how far the RF can go?
Yes.
Okay, well, that depends on many things. In most cases, the fiber that's fiber plant in the field is geared toward 1310 nanometers. So one can transport 3 or 6 gigahertz signals over tens of kilometers, 10 kilometers, 20 kilometers, 50 kilometers. for the lower frequencies. For the higher frequencies and those that transport at 1550 nanometers, the distance is not a problem with respect to the insertion loss of the fiber. The insertion loss is still approximately 0.7 dB per kilometer. However, at the higher frequencies, one needs to begin to worry about fiber dispersion. So in fiber dispersion, it's similar to group delay in an RF signal. In an RF signal, different frequencies travel at different speeds, essentially, through RF cable, group delay. So at higher frequencies and longer distances, we need to begin to care about or be mindful of dispersion in the fiber, where different parts of the signal travel at different speeds. But for lower frequencies, 3 gigahertz, 6 gigahertz, that is not a problem, and one can transport tens of kilometers.
Thank you.
Yes. So just to wrap up with the OTDR, when a fiber is broken, the SFP switches to sending pulses, and the SFPs measure the time delay of the sent and received pulse, and in this way, one can use the remote user interface on each side to estimate the location of the fiber break. So if you have an antenna that's 100 meters away, perhaps that's not important or a big deal. But in cases where one is using leased fiber or transporting over very long distances, that may be a useful feature. So I'll just check the time. I'll wrap up here in a couple of minutes. Just very quickly, I'll go over very quickly some more telecom sorts of applications, and I can certainly entertain questions offline. This is a simple GPS system where we have an outdoor box and an indoor receiver, where we can actually employ redundancy of fiber antennas. Let's see. Here's a case where we have 2 redundant antennas. We multiplex those onto a single fiber. We split those to multiple locations, and then inside of our fiber receiver, we can switch between a primary and a redundant antenna or fiber path. So this is a way to employ redundancy, primarily in wireless and telecom applications. Again, this is more GPS fiber transport to small base stations or small cells within a building, perhaps. We can transport the data either over the fiber or over Cat5 Cat5 twisted pair Ethernet. We offer a GPS tester. This is very useful for our customers to test their GPS over fiber. One may use this tester to connect directly to a signal, measure signal integrity and the number of satellites seen, and then take that same tester and test at the GPS receiver, and in that way test or verify the signal integrity after going over the fiber plant. A telecom application is essentially distributing a telecom donor antenna that's sitting on side of a building to wireless to re-radiating antennas inside a building. And then one last application is our Zonu Connect, where one may, in many cases, this is for primarily connecting to distributed antenna systems that are in convention centers or in stadiums. In that case, the telecoms have a base station that is located near the distributed antenna system. In many cases, it's not feasible to put a telecom base station at a hotel or at a stadium. So one may remote that wireless base station at a distance far away from the actual venue. So an example of a job that we recently did was at the Super Bowl for the National Football League Super Bowl in Phoenix, Arizona this year. There was not a base station at the actual stadium. There was a base station, telecom wireless base station at a nearby convention center. And fiber was actually used to connect the distributed antenna system at the stadium to a remote base station for connecting the distributed antenna system into the overall telecom system. So that's basically kind of an overview of optical Zonu, primarily Satcom types of applications and products.
Thank you, Britt. Now we have
Yes.
two more questions.
Sure.
Now the question is from one of our guests. How drones can handle the weight of fiber cable? Drones. Does it
Okay.
block the balance of the drone?
Yes.
Did you perform a real application for this case? If yes, what's the distance of fiber?
Well, we've worked with partners. Let me go back to that picture. We have worked with partners. We do not do drones ourselves. We provide the small little fiber optic transmitters and receivers. So the weight of our smallest, let's see, I don't know if I have the weight on here, but it's on the order of 15 grams, I believe.
Okay.
So I'm not answering your question well, but our smallest form factor, I think, is 15 to 17 grams for and actually this is kind of the payload on a drone. And this is one of our small fiber transmitters or receivers that's powered from 5 volts. So this has a certain weight, and indeed the fiber itself has a certain weight per meter. So indeed a drone has to be a certain size in order to carry that weight, even though it is minimal. It is certainly, depending on the length of the fiber, it is a consideration.
Okay, one more question.
Yes.
What RF power levels can RF over fiber equipment tolerate?
Oh, okay. Very, very good. And that's actually one of the actual signal levels are low. Let's see.
We have wonderful questions.
Yes. So actually that is one of let me show the picture here again of the base station. Radios handle powers, 1 watt, 10 watts, 50 watts. Well, we certainly, yes, that's an issue that needs to be addressed in fiber transport. Basically the maximum RF power level that can go into a fiber optic link and be linear is more on the order of 10 milliwatts. So in order to transport, those sorts of radios that are operating at multiple watts, one must attenuate the signal down to 10 milliwatts or less. And then I suppose that at an antenna, those signals have to be amplified back up. So that is perhaps a limitation of fiber optic transport. The signal levels have to remain below on the order of 10 milliwatts or plus 10 dBm.
The last question is the difference between CWDM and DWDM and their applications.
Oh, okay, very well. So CWDM is coarse wavelength division multiplexing. DWDM is dense wavelength division multiplexing. So they're essentially the same. They're essentially the same function. Basically converting RF signals to a particular wavelength. However, coarse wavelength division multiplexing, the signals are spaced apart by approximately 20 nanometers. So that's kind of a large spacing. And that is necessary because that is primarily for transporting with uncooled laser diodes. So when one is using an uncooled laser diode, there's not active cooling or there's no closed loop control of the temperature of the laser diode. And in that case, as the temperature of the actual laser diode goes up and down, the wavelength changes as a function of temperature. So the filtering, the CWDM filtering has to be much broader. So one cannot pack as many wavelengths into a small window. Now, dense wavelength multiplexing, that assumes cooled laser diodes. So those are more expensive laser diodes. They have their temperature controlled to a fixed temperature by closed loop control. So in that way, as the ambient or the environment, the temperature of the environment around the laser diode goes up and down, the actual temperature of the laser diode remains the same. Hence, the wavelength is stable and remains the same. So the filtering of the wavelengths can be much finer, and one can pack many more wavelengths onto a single fiber. Instead of perhaps 8 or 12, one may pack 36 wavelengths onto a single fiber. And that's not so much done in RF, but that's very much taken advantage of in data networks, digital and data networks. So functionally, they're the same. It's just the sophistication of the and the temperature control of the laser diodes.
Thank you. Last question.
Yes.
I see that you know this subject, fiber wavelengths, wonderful. But can you tell us, our audience, what's your studies? Did you like physics, mathematics when you were in secondary school, high school?
Oh, okay. Well, my background, a long time ago when I was in school, I studied electrical engineering. And my primary focuses were on actually digital signal processing and digital controls. But I got out of college and got a job in California doing basically in aerospace, doing basically communication systems. So that's basically, I've never done DSP, digital signal processing, the last 30 years. I basically got into comm systems and have done that ever since. And then about 20 years ago, I got into comm systems over fiber. Perhaps some of the audience that is familiar with fiber may remember the company Ortel. Yes. In the US. They're one of the pioneers of doing linear signal transport over fiber, and a big portion of their business was cable TV over fiber. So I actually worked at Ortel and EMCOR for about 10 years. EMCOR is no longer in the business of RF over fiber. So, and I've been at Optical Zonu for 3 or 4 years. So even though my background is in something different, I've always, since I got out of school, I've worked in comm systems and have done those sorts of things. Thank you.
Thank you, Britt.
Yes.
Thank you for joining us today. Now, Ladies and gentlemen, thank you for joining us today to explore the transformative potential of the RF transmission over fiber optics technology and the visionary work of Optical Zone. I encourage you to connect with their team to explore how this groundbreaking solution can revolutionize your business. I want to see you, all of you, in another Tech Days. Thank you, Britt, for attending this event.
And thank you to Profen for hosting the webinar.
Thank you.
Thank you for attending. Have a nice day.
Bye.